Hello and welcome to the final workshop. My name is Josef Schindler, and together with my colleague Yakin Kiran, we will talk a little bit about the IoT interfacing with an example of the battery storage. Yes. So first I will give a short introduction about the battery storage. What is the motivation of this minor project that we did inside DEcent project? Then Erkin will explain the communication protocols that are possible, and of those we chose one. And last but not least, I will demonstrate the implementation of the battery storage. Yeah, of course, we have this decent idea with a smart neighborhood where the cross-commodity market helps to use energy efficiently. And of course, we have EVs or electric vehicle chargers, which are the components that are connected to the power grids. The EV charging can happen in private households, which is exclusive, and in business areas where it is available for everyone. So we need to somehow reserve those, and we will have several charging stations. So there can be some problems from this. Maybe the grid capacity is not great enough. How do we organize it, control it, and who takes care of it? And what about the secure communication, especially from a charging station to a remote client or something like that? In Ettersdorf, we have, in general, we have a battery storage, which can be first life or second life battery storage. So second life would be recycled batteries, or yeah. Then we have a charging station to make this use case, and a control system, of course. And we have this limited grid connection. So the battery storage can then also supply energy to the charger if the electric vehicle wants to consume more than the grid can provide. So here's again the decent idea with a trading agent and the local market. So the charging station can interact with this. And of course, as I explained before, we wanted to have a reservation system. So the charging station is blocked. But which machine-to-machine communication protocol should we use? This will be explained by my dear colleague Yakin Kiran.
Yes, I hope you can hear me. My microphone is working. So yeah, an umbrella term, machine-to-machine communication. These protocols, OPC UA, MQTT CoAP, you have seen maybe in the slides here or there, and also you will continue seeing, especially MQTT and OPC UA in the DEcent project. So these are like three the most common machine-to-machine communication protocols. This list can go further, like you can add the XMPP, AMQP, etc. But these three are like the common standards today. First, let's compare them between each other. For example, to give an overview, OPC UA is pretty much a standard for industrial automation. Yeah, it is widely used in PLCs, in factories, and so on. It's really a standard right now. There is MQTT and CoAP. These are more lightweight options because OPC UA is pretty heavy and a feature-rich protocol. MQTT is lightweight, and it's basically a publish subscribe protocol. Very simple, very easy to use. If you need a publish subscribe, then you go for MQTT. That's why it's also used a lot in IoT, having constrained devices like microprocessors, microcontrollers. There is also CoAP, which is an HTTP alternative, which is a lightweight version of HTTP. It is newer than MQTT, and it is somehow less popular than MQTT at the moment. So in the further slides, I will tell you about in each these three protocols, the research we have concluded as part of the DECENT project. So with OPC UA, we have completed two research tasks. The first one is open source OPC UA security and scalability. So the key result, our aim was, okay, there are some open source OPC UA implementations, but how about their security and scalability features? Do they overlap, conform the standard, etc.? So the key result is we detected like 4 really popular implementations in various languages, and they conform the standard quite well, and their scalability change drastically, mostly based on their languages. So yeah, you can basically look at the work. It's published in EDFA to look at which scalability is better or worse in which implementation. The second one is feature-based comparison of the open source OPC UA implementations. There we mostly focused on the features and functionalities that these implementations offer. There is an ongoing research. It is not yet completed. It's yeah, pretty much a lot of progress there, but it's not completed at the moment. OPC UA pops up over TSN. So the early results show that the different queuing disciplines are more suitable for different requirements and traffic patterns. With MQTT, we achieved to complete one research task, which we call open source MQTT evaluation. There we look at the trade-off between resource consumption and network latency among different implementations. The network latency is mostly caused by randomly randomly drop the packets. That's why you have to retransmit, and then the network latency is changes between the implementations. It is also published in CCNC, I guess in January, yes. So 3 months ago, it was also, I presented in the conference. There's one ongoing research, it's also almost done. TLS cipher suite performance on MQTT. So, okay, we want to secure MQTT, we have an options, we can use TLS, but which cipher suite is better here? Because every cipher suite comes with trade-offs. So we look at resource consumption, and which also can be optimized through the choice of cipher suite, as well as adjusting the length and the rate of MQTT messages. Finally, in CoAP, there is one ongoing research. This was also almost at the end, the assessment of security mechanisms for CoAP. So ideally, CoAP is secured with DTLS because it's a UDP protocol. But there is a new RFC 1 year ago published, which proposes OSCORE to make it lightweight security for CoAP. So the early findings show that there are advantages of OSCORE, as well as some vulnerabilities, like OSCORE has some privacy issues because some header fields are not encrypted like DTLS. So there is again a trade-off that we hope to present in the research here. That's all. I gave an overview of the concluded research tasks and published as part of the DECENT project. Some of them are ongoing, 2 of them are ongoing, the others are completed. And this is the overview of the machine-to-machine communication protocols that I've been mostly busy with so far.
Josef, you are still muted.
Sorry, yeah, of course, the muting always. Thank you, Erkin, for this short introduction on the communication protocols. And now, as promised, we will have a short demonstration where we implemented OPC UA for the use case of the battery storage with a charging station. As you can see here on the left side, there is a screenshot from the HMI. On the top, you have the limited grid connection as it is to be found in Eltersdorf. Next, we have the battery booster and a charging station. And as we have a simulation here, the electric vehicle plugging and stuff can be done on the HMI. And we also have a simulation so we can speed it a little bit up. Otherwise, the charging processes would take too long to show them here. Next, we have the control panel. It basically has all the functionality a typical charging station has, and it also reflects the charging station that we used from Kiva. And here is some historical and current data on the charging process. As you can see, on the left side, we have the PLC overview, so it reflects the current state of the physical model of the electric vehicle and so on. And it contains also an OPC UA server. On the right side, we have a generic application with an OPC UA client, and it can remotely access data on the OPC UA server and do stuff. For example, we can view the state of charge, as in the first demonstration video. On the left side, we have the state of the charge at the PLC, and on the right side, we have the state of charge at the application. And as there is no charging process at the moment happening, the grid charges the charges the battery, and we will see this on both sides. Yeah, next we can do a reservation of the charging station. Again, on the right side, we have the client. So we do the reservation. We choose a time, for example, which is hopefully in the future. Yes. And we choose a date, for example, and then just get the reservation with the RFID, and the server response says the reservation was okay. So on the server side, we will then have the reservation reflected here on the left side, where the reservations are presented, of course. Okay. Next, we start the charging process from the client when there is an electric vehicle plugged to the charger. We can then just start the charging from the application, and we get the feedback from the charger, of course, and the charging happens physically. Yeah, as you can see, of course, time is happening, and the electric vehicle will be charged then. But we have, for example, also this RFID, and if it does not, it is not the same as the reservation says, then the charging process cannot be started with the RFID. So we have this reservation functionality here. As you can see, if we change the RFID and we want to charge, then the server says, no, sorry, someone else reserved the charging station at the moment. And if we change the RFID back, the charging once more starts and everything is okay. Yes, that's it from my side so far. Thank you for the attention. I think I will hand over to the next presenter.